Oh, that's new. So you got an audio announcement now that it's being recorded. That's pretty slick. Let's see. I want to do a couple things here. First off, I'll share my screen. Maybe. Can you still see my screen okay via Mozilla Firefox?
No, I can't see your screen.
Something weird happened there. Let's do that again. There we go. We're back. Now that looks familiar. So now I'm guessing you can see it. First thing I want to do today is just kind of go out to D2L just to show everybody kind of the layout that I go through with that. So it's easy for you to find where things are at. This is what D2L looks like for me when I get in there. And here's ME316 for the summer semester. That's nice that that loaded. How about I hit the refresh button? There we go. So in D2L, I guess the main things are, I do have the syllabus listed over here on the left widget. And with our meeting on Monday, I realized that the course description was updated from summer 2020. And so I did go through and update the syllabus. One thing that you'll potentially run into is that this gets placed into your cookies or cache or whatever. And so you would have to delete your browsing history to see the new version show up. So just be aware of that. But the only thing that changed when I uploaded that on Monday was that course description. There's the link to my page on the School of Mines homepage. And then most everything is found here under the content tab. And I have these broken down into lectures now. I have to move some stuff out of the way for me. But what I'll do is just make submodules for each of the lectures. And so for a Monday lecture, I had the lecture notes uploaded. And then afterwards, that Monday afternoon, I uploaded the video. And then for today's lecture, I've done the same thing. I've uploaded the lecture notes. Following our discussion here today, I will upload the video as well. One of the comments that I've had from the past in the students is they like the videos uploaded in this manner. What I do is I record to my computer so that I can upload that as a file to the content folder. That allows you to download the video to your computer. I've heard if it's saved to the cloud, it can be problematic. If you have wireless connectivity issues, it'll pause the playback of that. So students really like that they're saved as files and uploaded so that you can download those and not have to worry about delays in watching that. Next up, I'll have another main module, which is our homework folder. And so I did go ahead and post our first homework out there. That'll be due not this coming Saturday, but next Saturday, June 19th by 11:59 p.m. Mountain Time. And so these are just completing the problems from your Hibbler textbook. Engineering paper is preferred, but I know that's only easily accessible through the School of Mines bookstore, some other places. And so I'm not going to hold that as a firm requirement on the paper that you used. Just the main thing that it's nice, neat, and organized. Making sure to use the given find analysis procedure for each of the problems there. And then place a box around your answers for each of the problems. But this is placed out as a drop box. And so it's a new drop box that's added. So then you should be able to see that show up as a drop box where you're able to upload that PDF file then. And so after you do your homework, scan that in as a PDF file and then upload that file to the Dropbox. Let's see, are there any questions over kind of the layout of D2L or questions in regards to completing the homework?
I do have a question about it. On the syllabus, it said you would have a document for the format and stuff for the homework, I think.
Yeah, and that's going through like that given find analysis procedure. I'll get that uploaded to D2L. That's something that the mechanics faculty put together here a number of years back, but I'll go ahead and get that uploaded to D2L so you're able to see that. But really it just is that given find analysis procedure and putting a nice box around the answers essentially.
Okay, thank you. I just transferred, so that's why I'm not familiar with it.
Okay, that's totally fine. Thanks. And then are there other questions? All right, so we'll call that good there. Always like to navigate D2L and make sure everybody's comfortable with that. And now we'll go through our lecture notes for today. And again, this is kind of review from statics, from introduction to solid mechanics. And so this will get you all squared away for that homework that's due next Saturday. We'll also have some lecture notes on Friday that will be necessary for that homework due next Saturday. But review stuff, chapter 1 of Hibbler really just deals with stress. And you kind of looked at those things last year or last semester in ME 216. But you have different types of stress. You have a normal state of stress, which is commonly obtained through axial loading. And with the axial loading, if you're looking at a circular or rectangular bar that you're just placing a force on to pull that or compress it, you're really looking then at an average state of stress that develops within that cross section, which is just simply the axial or normal force divided by the cross-sectional area of that axial member. The main thing about that is that average state of stress is really only valid away from that point where that loading is applied or where that's gripped. You can end up with stress concentrations where that item is gripped to pull on it or push on it. And then remember with St. Venant's principle, as you move over a distance about 3 times the order of magnitude of the cross section dimension, those stress concentrations fade away and you develop that nice average state of stress through the cross section. I mentioned that on Monday too. I like to use capital P over A for the axial load, and A is the cross-sectional area. But that axial load also represents then a normal force. And so sometimes you'll see P, that capital P replaced with the capital N, and Hibbler does do that. So you'll see that in your textbook that they use it in there instead. But the thing that causes confusion with that is when you're using SI units and the force is in newtons, you're solving for N is equal to some value in newtons. So I kind of like P in that regard. It only gets confusing then when you add pressure, so you have to be careful on that. And so that's normal stress. Then direct shear stress, say if you have two surfaces that are bonded together and then you have a shearing force placing a shear on there, you end up with the same thing. An average shear stress across that bonded surface is just that shear force that's being applied divided by that shear area. And for that, I do subscript that with an S for shear area. In some instances, it's just really that surface area where the bonding occurs that represents that area. In other situations, say for example, if you have a pin going through something and the pin is being sheared, it would be the cross-sectional area of that pin. So in some cases, it's the bonded area. In some cases, it's the cross-sectional area. It's just a matter of where that shear stress is transferring through. Bearing stress is also looked at. That's really that compressive stress that develops through like pin type connections. And it's really just that force divided by that projected area of contact. Again, which is just a compressive normal stress at joints and pins. So in general terms, stress is a force per unit area. And that's true with all of these. We find all of these are a force per unit area. And if you're using the SI system, the base units are Newton for a force and a meter for the length value. And so the unit of stress then would be 1 Newton per meter squared, looking at a force per unit area. And 1 Newton per meter squared is equal to 1 Pascal. So a special name given there for that unit. And then in the English engineering system, we have for the force of pound, and the length value of inches is common. So you end up with a pound per inches squared for a force per unit area, or 1 PSI. And there are 6,894.8 PSI per pass, other way around, per Pascal. And so, yeah, there's 6,894.8 pascals in 1 PSI. Then just some other things to be aware of then with unit systems is that we're generally dealing with really large numbers when we start talking about the state of stress, the Young's modulus of the material. And so the Young's modulus of steel, for example, is 200 times 10 to the 9th pascals, 200 gigapascals. And in the English system, that's 29 times 10 to the 6th PSI. And so as we're going through calculations, if we're using base units, we're going to have to be dealing with scientific notation and keeping track of all those exponents, which can kind of be a little bit time consuming in that process of writing things out all the time and always having to deal with the scientific notation. And so if we decide to use different units rather than our base units, we can have different units coming out of that. And so this is one thing I always kind of discuss, even back as far as ME110, but same when I taught ME216, that if you use a unit of force of a Newton and your length values in millimeters, I think when we're designing things, they're generally a little smaller in size, so millimeters is actually a little bit nicer to be on your drawings than a really small number in meters. But if we look at that and look at the force per unit area, 1 Newton per millimeter squared, there's 1,000 millimeters in 1 meter for unit cancellation. We have to square both of those terms. And so the 1,000 gets squared along with the units. And so that works out to 1 million then Newton per meter squared, which is 1 megapascal. And so that then is a little bit nicer if instead of using newtons for your force and meters for your length, if you use newtons for your force and millimeters for your length, your stresses and your Young's modulus values would need to be then in megapascals. And so instead of that 200,000, 200 times 10 to the 9th pascals, you could put 200,000 in place of that and not have to deal with the scientific notation. And then likewise, the units of stress, they're generally going to be in the megapascal range. And so the strength of steel is really also around that 200 to 250 megapascals. And so then you see you're not dealing with a lot of digits then at that point. And so that kind of eases things from just the flow of it, of not having to deal with scientific notation as much. And I've used different unit systems before as well, with maybe micronewtons or microns, micrometers, just depending on the scale of the application that you're dealing with. And so that's generally what you will look at in deciding what units you want to use, so that your units of stress come out nicely based on the problem at hand. Then you can do the same thing in the English engineering system, where they have defined a kip. 1 kip is equal to 1,000 pounds. And therefore, 1,000 PSI would be equal to 1 KSI. And so same thing, instead of having to deal with that 29 times 10 to the 6 PSI, if we're looking at the Young's modulus of steel, that would be 200,000 megapascals or 29,000 KSI. And so we're not having to deal with as many significant figures. And then for like A36 steel, for example, that yield strength is around 36 KSI. That's the A36 designation. The 36 represents the yield strength of 36 KSI. And so, hooray, we don't have to have a ton of digits in that expression when doing so. I guess questions, do you have any questions on the unit systems at all? Are you pretty comfortable with that? And then the other thing too is we'll be doing this as we go through example problems too, just to show kind of a nice unit system to use and going from there. I think another thing that will show up is a force in kilonewtons and a length in millimeters. So if you're in kilonewtons and millimeters, the Young's modulus and stress would be coming out as gigapascals. And so you'd only have to use 200 gigapascals in your calculations. So I think we're good there. Then also concept in ME 216 is developing that stress is a tensor. And so you have a full 3D data stress comprised of your normal stresses, sigma X, sigma Y, sigma Z, and your shear stresses. tau xy, tau yx. This matrix is symmetric, so tau yx would be equal to tau xy. And this is for materials that are isotropic in nature. They have the same properties in all directions, and they're homogeneous as well. So they're the same throughout the entire deal. If you start developing anisotropies, things like that, you can have more complex, essentially stiffness matrices that are required to look at this stuff. But if we look at first an example problem of axial and direct shear, we are given, say, a coupling between a 2-inch diameter rod and a 1.5-inch diameter rod. And what we're asked to find is the minimum length 1, L1, and L2 if the average shear stress is to be below 500 psi when the force P that is applied is equal to 8,000 pounds. And then 2, we're asked to find what the normal stress is in the smaller rod. That would be the greater state of stress in comparison to the larger diameter rod. And so going through, again, this is kind of what I'm expecting on homework is given, draw a diagram, find what are you finding, and then analysis. You may have some assumptions that are needed. In this case, we're assuming that there's no bonding on the circular faces. And so these are circular tubes going into this connection, but there's no bonding on those circular faces, just along the circumference. And so analysis for that 2-inch rod, the average shear stress would be equal to the shear force over the shear area. And that shear force is just going to be equal to the axial load that's applied. If you were to draw a free body diagram of this, you just have a shear force acting in the opposite direction. And so some forces in the X, that shear force would be equal to P. And the shear area is just the circumference of that. So pi times diameter times L1. And so with that, our constraint is keeping the average shear stress less than 500 PSI. And so we can rearrange that to solve for then the L1 that would be required to maintain that shear stress less than that point. And I see an issue with units that I did here when I was redoing these last summer, but L1 is going to be, oh no, I'm good with units. I see what I did. L1 is then our shear force, 8,000 pounds, divided by pi, divided by diameter, 2 inches, divided by the shear stress, and it's 500 pounds per inches squared. So I put inches squared up in the top so we could see the unit cancellation taking place. And pounds cancel, and 1 of the inches will cancel on top to leave us with inches in the units. And everything comes out to 2.55 inches for that minimum length required to keep the shear stress below 500 PSI. For the 1.5-inch rod, it's the same thing, except you're replacing the diameter with 1.5 inches. And we end up with 3.40 inches for that minimum length required. Then the average normal stress in the smaller diameter rod is just the force divided by the cross-sectional area. And that cross-sectional area is pi d squared over 4. And so we can place our values in there, 4 times 8,000 pounds for the load, divided by pi, divided by the diameter, 1.5 inches, quantity squared, will give us 4,530 PSI. And I just put the yield strength of some materials, polycarbonate, 9,000 PSI, A36 steel, 36,000 PSI. And so that's fair distance below that. So any of those materials might be sufficient for that application depending on the factor of safety that you want. But that was just a quick example just to highlight both the axial stress and the direct shear stress. Any questions? Yep.
Scroll down on the derivation for the second part of this problem. Where does the 4 come from?
Okay, so we're looking at a cross-sectional area. And remember, the area of a circle is pi r squared. But the radius is just the diameter divided by 2. And so if you square diameter divided by 2, you end up with diameter squared divided by 4. So pi d squared over 4.
Okay, that makes sense.
Yep. And so, yeah, we're just solving the area of a circle there. And that's common. I think what you learn really early on about areas of circles is they're pi r squared, but then in practicality, you'd never measure the radius of a cylinder. You'd always measure the diameter of the cylinder. So that's kind of the value that you tend to measure. Then we can move on then to chapter 2 that deals with strain. And we have then an average axial strain. And looking at the parameters here, we're talking about an axial loading condition. We're showing tension here where we have a load P stretching this out. And so we have the original length L0. That's going to stretch to a final length L final. And the corresponding displacement then that would occur would be equal to L final minus L original. We have also a change in cross-sectional diameter and cross-sectional area. So if you pull on something and it stretches, it's generally going to go from a larger diameter D0 down to a smaller diameter D final. And so then your average axial strain then is just simply your final length minus your original length divided by your original length. And LF minus L0 is the displacement over the original length. And oftentimes then the original length is also referred just to as L. And so delta over L would give you your strain in your axial direction. And so I think from a concept standpoint, I like with having the F and the O subscripts, but in practicality, those subscripts are often dropped and you just realize that the L that's being requested is that original length. Then if you look, that's going to be the axial strain. But then you have in the Y direction, the transverse strain that develops. And so that transverse strain would be the final diameter minus the original diameter divided by that original diameter. And so a delta D over the original D. And again, removing the subscripts, just a delta D over D is equal to that strain in the Y direction, which would be the transverse strain. And remember, the final diameter is smaller than the original diameter. And so that's going to cause delta D to be negative when you apply an axial loaded tension. And so you'd have a positive axial strain and then a negative transverse strain. And so I have that note there. For tension, strain in the X is positive and strain in the Y would tend to be negative. That's really for most common materials that would exhibit that type of behavior. There are weird things that as you pull it in tension, it will expand out. And that's really due to the network of the geometry and how that behaves. Probably the best example that you can relate to is those spherical balls, for example, that as you pull on it, it just expands out to a bigger sphere. But they can also do that in terms of actual materials and the microstructure that's developed there to cause an expansion in that transverse direction, even when you're pulling on it. To do so, you're just creating larger voids within that. And so we tend not have to worry about that because we tend to make things out of solid materials or tubes or things like that. So we're not dealing with microstructural changes in geometry. But this was kind of presented in terms of a circular cross section, but the same applies to non-circular sections. Say for a square type cross section, HO would be your initial height or original height, and HF would be your final height. You can calculate the strains based on that. But both of those are normal strain conditions, and so they act in the normal direction. And then if we look at signs and units in relation to that, axial strain, epsilon, does really result in a change in volume for the object. It generally is not going to, say for example, contract as much as it expands, and so there's going to be a small change in volume in that process. And then if we look at that definition of strain, it's really a change in length over the original length, and so it is unitless. But whereas stress and Young's modulus values are usually large values, strain values are generally going to be super small. And so sometimes units are defined as their values that you're calculating it with, like inches per inch. Still unitless, you're just telling what units you were using in the process to calculate that. But then a sleight of hand trick is to not have to deal with scientific notation. You can put a micro inch per inch, and that'll then take care of your scientific notation where you're dealing within 100 micro strain. And so that would be 100 micro inch per inch. And you can do the same thing with the SI unit system with that sleight of hand on defining units for a unitless system. But then for these normal type of strains, a tensile strain then is positive, that causes elongation, and a compressive strain is negative, that causes contraction. And then shear strain, dealing with results of shear stresses, that type of thing. You look at that from a different perspective. We have our shear stress arrows drawn on here. And so this is a stress element now that we've kind of taken out of a object that's subjected to pure shear, and the shear stress arrows have caused that to deform in that orientation. Whereas the normal strains cause a change in volume, this does not result in a change in volume, it just results in a change in shape. And so first thing we can look at is the average shear strain that develops at point P. First thing is the true definition of the shear strain is just looking at this lateral displacement, this shear displacement over that perpendicular original length. And so the average shear stress then is just that delta S over L0. And if we define phi as this angle here that develops, the tangent of phi is equal to delta S over L0. And so our average shear strain is equal to the tangent of phi as well, if we were to see that angle. And remember, tangent of phi is the same thing as sine of phi over cosine of phi. And then our shearing strains are generally very small, so that when you're dealing with really small angles, sine of a really small angle is approximately equal to that angle. And the cosine of a really small angle is approximately equal to 1. And so that would replace sine of phi with phi and cosine of phi with 1. And these are approximates now, so that would be approximately equal to that angle phi. And so that's one thing to be aware of, is just that transition along, and that our average shear strain is going to be approximately equal to that phi value, that angle. But as the shear strain gets larger and larger, it's going to diverge away from that angle and equal then the tangent of that angle. Let's see. Another thing to note is that if the average shear strain is approximately equal to phi, sometimes that small angle can be more difficult to measure. So that would also be approximately equal to pi over 2 minus our angle theta here. And so if you know theta, you could approximate what the angle phi is. And so units and sign on this, again, shear strain is defined by gamma. And again, it results in a change in shape, but not a change in volume. Its units are, again, unitless, but it's defining an angle. And so radians is a unitless angle definition. And so we wouldn't want to use degrees at all to define the shear strain, but we can use our radians for that. And we can also do the same sleight of hand trick, where if we use microradians, then we take into account that it's a super small value, say something like 200 times 10 to the minus 6th radians. We can just call it 200 microradians. And for shear strain, that's going to be positive if that angle theta on this face is less than pi over 2. And then it would be a negative shear strain if that angle were greater than pi over 2, say if it was shearing in this direction. That would lead to a negative shear strain. And so we have an example of this. Shear strain example, we're given a thin rectangular plate, uniformly deformed as shown. And we have the original lengths 500 millimeters and 250 millimeters. And it deforms in both directions. And so this section displaces over 0.2 millimeters. And this section at Q displaces upward 0.38 millimeters. And so we actually have two angles, phi1 and phi2, that we're dealing with in terms of the strain. And we're asked to find what gamma xy is at point P. And so by default, the exact value would just be the sum of those shearing displacements divided by the original lengths. And so it'd be 0.200 over 250 millimeters plus the 0.380 millimeters over 500 millimeters would give us 1.56 times 10 to the minus 3. And so that's not taking into account the solving for the angles phi1 and phi2, that's just solving exactly for what that shear strain is based on the definition. And so gamma xy again is 1.56 times 10 to the minus third radians. And so if we multiply that by 10 to the sixth, that would give us 1,560 microradians. And so that's the exact average shear strain at P. And so if we were to look at that in terms of just the angle alone, the average shear strain is equal to tangent of phi. And so phi would be equal to the inverse tangent of gamma average, which would give an angle of 1.559998 times 10 to the minus third radians, which is fairly close to the 1.560. And so I think that just kind of clarifies that difference between the shear strain and the resulting angle. We see that the shear strain is fairly close to then that angle that's defined there, out to the fourth decimal places, where we see the differences start to show up. But we can see that the average shear strain is approximately equal to that angle theta for our small strains that we have here. Any questions there at all? All right. Chapter 3, some of this stuff will probably move through fairly quickly because you've seen this before in MET 231, 232, and then again in ME 216. But chapter 3 really deals with material properties and the stress strain relationships. But we really need a way to relate stress to strain using that. And the main thing with tensile testing, it really depends on the length of the material and the cross-sectional area. So if we were to plot like force versus displacement for a variety of samples, we would get different linear curves if it's a linear elastic material, up to yielding and then up to failure. So the slope on these would be equal to the stiffness of that material in Newton per meter or pound per inch. The area underneath is the amount of work done to stretch that in the tensile test. And if we look at A1 would be greater than A2 would be greater than A3. It would cause more force to break that, and we'd have a higher stiffness associated with that. And so what they realized several centuries ago is that there's really no similarities in this force versus displacement for the same material. And so you really can't define stiffness as a material property since it varies based on geometry. So no similarities with the same material, but if you plot stress versus strain, instead of force versus displacement, all those different lines collapse onto the same curve for the same material. And so this is engineering stress and strain. Sigma is going to be your load that's applied over your original cross-sectional area, and your strain would be your displacement divided by your original length. And so all these collapse in onto the same line for a given material, and that slope would then be equal to the Young's modulus of the material. And then since these are being related back to the original length, what happens is necking occurs, that as you're pulling that in tension, you have your gradual decrease in the cross-sectional area, but eventually there'll be like a location of weakness where it really starts to decrease in cross-sectional area at that point of weakness until it eventually fails. And so since we're not accounting for that greatly reduced cross-sectional area, we see the engineering stress and strain drop off because we're dividing that by, again, the original cross-sectional area, not the current cross-sectional area. if you were to plot the true stress versus true strain, dividing by the actual cross-sectional area, you'd never see this drop down. It would just be a continually increase up to the maximum state of stress of failure. From a practical standpoint, we really don't want to design things to fail. And so we're operating typically well below that yielding range so that we're in the linear elastic region. But this really provides us then with 1D Hooke's law, where we can relate stress to strain just with this slope. The stress would be equal to the Young's modulus times that axial strain, which is 1D Hooke's law. And so, yeah, Robert Hooke was the one who discovered that linear relationship between stress and strain in 1676, a number of centuries ago, but it wasn't until about another century later that Thomas Young was the one who defined that proportionality constant, E as the modulus of elasticity, or Young's modulus. And so that's why we know that as the Young's modulus and why we know this as Hooke's law. But that Young's modulus then has the same units as stress. Since strain is dimensionless, that gets our units to be the same on both sides. This is kind of the standpoint where you see it in MET 231, 232. And it causes me concern in that typically we're going to be dealing with multi-axial states of stress. And so we're not really able to use this 1D Hooke's law very often. We need to use the full 3D Hooke's law, taking into account Poisson's effect within that constitutive relationship. And so we'll talk about that as we continue on. Before we do so, we have the same type of relationship for the shear stress and the shear strain, where that proportionality constant is defined as G, which is the modulus of rigidity or that shear modulus. But both of those describes the relationship between stress strain and shear stress, shear strain within that linear elastic limit. Again, it's referred to as the engineering stress, since related to that original cross-sectional area or original length type stuff. And then true stress depends on the force over the current cross-sectional area. And so you see my notes that I usually do in class. I'll usually just plot the true stress versus true strain, but that just keeps increasing until it fails. And again, since we're dealing with mainly this lower portion, we're generally not concerned with true stress, true strain. And so that ends up being more of a graduate education topic when you start dealing with the plastic behavior of material. And so this initial region would be known as the linear elastic region. And then past that would be plasticity and trying to understand that progression to failure. But there's a whole lot of other different quantities within this engineering stress strain. There's an ultimate stress, that maximum value that it reaches. There's the proportional limit and the yield strength. The proportional limit is just when that stress versus strain just starts to become nonlinear. And then that yield strength is defined as a 0.2% offset. So 0.002 would be the strain level, and just run that up at that same slope as the Young's modulus, and where it crosses the engineering stress strain would define what your yield strength is. And so with that, it's the yield strength that you commonly use for design purposes, along with your associated factors of safety to stay well below that. So there's a picture of that necking that would be occurring, slip along 45-degree planes that causes that drastic reduction in cross-sectional area. There's some other values looking at the area under the curve. Remember, for force versus displacement, the area under the curve is equal to the amount of work done needed to cause that displacement. For stress versus strain, the area under the elastic region is known as the modulus of resilience. And then the area under the entire curve is known as the modulus of toughness. And it really just relates then to how much the material can stretch and how much strain energy can be absorbed in that process. And there's other measures on ductility, percent elongation. Mild steel is about 38% that it can elongate. So you can see that's equal to the strain. So a strain of 0.38, whereas gray cast iron is really brittle. And so it can only go to about 0.006 strain or 0.6% strain. And then it fails in a brittle manner. You can also look at percent reduction in area. Poisson's ratio is another material property that is extremely important. Again, when you're dealing with multi-axial loading, or just to learn what the transverse strain is. Our Poisson's ratio is defined as a negative value of your transverse strain divided by your axial strain. Remember, again, when we're talking about that, when it's in tension, the transverse strain will be negative and the axial strain is positive. And so the negative out front causes the Poisson's ratio to be positive. And that's going to range generally from 0 to 0.5. When you start dealing with ceramics and concrete, that type of thing, you're looking at Poisson's ratio around 0.2, plus or minus about 0.05. Steel and other metals are generally going to be around 0.3, plus or minus about that same 0.05. Then when you get into polymers and things like that, you're generally around that 0.35 to 0.4 for the Poisson's ratio. And then when you get into rubber type materials, you're in that range of 0.4 to 0.5. And then as you're dealing with plastic effects, once you get into the plastic region, no matter what your Poisson's ratio was in the linear elastic region, it generally will shift to that higher end 0.5 after it yields. And then for those odd materials that I mentioned, like the spherical ball, as you pull on it, it expands in all directions. That would have a negative Poisson's ratio. And they can do that from a microstructural standpoint, but again, it's not very common from a practical standpoint. And so now we get into Hooke's law for a general state of stress. Again, we're dealing with a linear elastic material. Isotropic, same properties in all directions. And the general 3D Hooke's law is really kind of easy to remember. It's really just looking at the subscripts within each one of these. We have strain in the X. All these will start out 1 over E times that stress in that same direction. So sigma X minus nu times the quantity of the stress in the other 2 directions. And we see the same thing with strain in the Y. You're repeating that subscript sigma Y minus nu times the stress in the other 2 directions. And so this 3D Hooke's law is still pretty easy to memorize, just seeing that pattern there. And so this is the one that I prefer you then to remember when you're dealing with uniaxial loading conditions, sigma y and sigma z would be 0 in those cases. And so it would collapse back down to the same 1D Hooke's law. You would have, if you multiply through by E, sigma x is equal to E times epsilon x. And so you can get 1D Hooke's law out of this if your sigma y, sigma z are 0. Let's see, over here on the right, there's just a little comment going on where we look at the normal stress for axial loading condition, P over A is equal to the Young's modulus times the displacement over the length, our strain here. Remember, strain, displacement over length. And so two things. One, the stiffness of the bar would be equal to P over delta. So that's a delta value. And that is equal to EA over L. And so when we relate back to the force versus displacement plot, we can calculate out what the stiffness of that would be based on the Young's modulus of the material, the cross-sectional area, and the length. And so that's handy to be able to see that that stiffness that varies with respect to geometry is a function of the material property and the geometry. Likewise, you can rearrange for this to solve for then the displacement. The displacement would be equal to P times L over EA. And that really gets into then the crux of the next chapter dealing with axial loading conditions, making use of that. Let's see. And I think what we can do is stop the sharing for a second, and we can take a 5-minute break. I think it's nice to take little breaks along here when we have a full 2-hour class period so we can get up, move around. I can answer any questions that you have. Do you happen to have any questions?
No, I don't have any questions yet.
Okay, and since it's just the two of you, do you want to take a break or do you want to just keep trudging along through the rest of it?
Yeah, I need 5 minutes.
Okay, I was going to say it's nice to have a little break there. And so I'm going to stop recording for a second and then I'll restart recording when we come back on.